So basically what Einstein is saying is, I'm standing still, I see you flying by me. While I see you flying by me, your clock is running slower. Now you would think then that as I'm flying by, that person would look at me and see my clock running faster. Equal but opposite. But that's not what Einstein's saying. Einstein's saying even though one party is to be considered motion and the other one is to be considered stationary, from the perspective of each, the other clock is actually running slower simultaneously. Very difficult concept to grasp because it flies in the face of every comparison that is typically equal but opposite. In this case, it's equal and the same. Right? But it does preserve the concept of relative motion and Galileo's principle. The traveling brother will experience gravity while his spaceship turns around. He will see his brother's higher Earth clock running much faster than his own lower clock during the acceleration phase. So even though the clocks are in an equal but same situation, the key is the turnaround here, because during that turnaround, that person is experiencing gravity. Just to give you an example, if we were talking about riding in a car as opposed to a spaceship, you'll still feel some gravity, you'll still feel some acceleration, some force. If you go into a turn very quickly, what happens is your body kind of goes up against the car door as you're going around that turn very quickly. So that is, you're actually feeling the acceleration from the change of direction there, and that is just another case of simulated gravity as far as Einstein is concerned. Now put that in a ship that's going 9/10 the speed of light, and that's a lot of gravity, a lot of g-force during that turnaround, and because a field of acceleration or a pseudo-gravitational field is actually manufactured during that turnaround, then what would be true in a gravitational field should also be true here. And so Einstein is saying that the person who's in the vicinity of this induced gravitational field, they would be considered to be in the lower clock position. And just to show you, that's the lower clock position, which goes slower. The higher clock position, which is farther away from that field of gravity, goes faster. So that's what he's saying. The traveling brother will experience gravity while the spaceship turns around. He will see his brother's higher Earth clock running much faster than his own lower clock during that acceleration phase. And it's that kind of undoes the paradox, because even though these are equal but the same, this is that equal but opposite effect we're looking for that more than compensates for this constant velocity portion here. The Earth brother will see traveling brother's lower clock running slower as he views the turnaround due to equal but opposite time rate changes. And by the way, both of these things aren't viewed simultaneously from each party. There's something called the relativity of simultaneity, and it's often exaggerated in terms of its analysis of the entirety of relativity. But here's an actual real effect of the relativity of simultaneity, where this person will actually experience something at a different time than this person, because those light waves will actually take time to go from one person to the other. The person that's actually turning around is experiencing the instant gravity, will feel those effects right then and there, where it will take time for that effect to catch up to this person. It will be an equal but opposite phenomenon. It's just that it's not going to happen at exactly the same time during the turnaround, because those light waves take time to get back to Earth. So it'll be equal opposite with a lag. Okay. So it exploits that Einstein's relativity has not one, but two separate motion-related time dilation mechanisms. Very interesting to us here, because if we're trying to figure out what time is, then we want to study relativity, because there's time dilation and relativity. But a second interesting fact is that the type of time dilation that's enacted during constant velocity must be an entirely different type of mechanism, time dilation, that's enacted during the acceleration phase or the gravity phase. And how do we know that? Because the behaviors are different. In one case, we've got equal effects that are the same, symmetrical or reciprocal. I suppose we can use, those are two terms that are used to describe that. But during the turnaround, which is a gravity, a pseudo-gravitational field or gravity-induced field, it's actually equal but opposite. So we know that, amazingly, there's not one but two motion-related mechanisms. And so important we have to repeat it, right? If Einstein's relativity is correct, then amazingly we have not one but two completely different motion-related mechanisms for how time dilates in the universe. Does this theory provide a real mechanism for time dilation occurring during constant velocity? And actually, the more we think about it, the more we will have to say no. Our ultimate quest here is to see what kind of mechanism, if any, is behind what we experience as time. So we talked about the mechanism behind temperature, the mechanism behind what produces color. In this case, we're looking for some sort of underlying cause for what produces what we feel and what we know as time. We're looking for clues with special relativity's ability to show that time slows down, but we can't really trace a mechanism to the act of constant velocity, because we know that for the other party that's in motion, they will view this other party's time as slowing down also, but yet B's clock didn't move a muscle. B's clock never sped up, never slowed down, didn't move at all. So really the best that we can do is that we can say is that time dilation is a co-effect of relative motion if we subscribe to the entirety of Einstein's relativity, okay? Is there a real mechanism for how time dilates in an accelerating frame? Well, again, in that case, it's very tempting to say that there's a mechanism, that being the acceleration itself, but upon closer analysis, we can't say that there's a mechanism there either, right? And the reason for that is that if we go back to our example here, this whole thing is traveling as an accelerating system, right? This accelerating system here is all traveling with the same g-force. So whatever gravitational or acceleration value we have on the ceiling, we have that same value on the floor. So they're traveling with the exact same g's, but yet their clocks run differently with respect to one another. What that shows is that, like our description of time for constant velocity, it limits our ability to develop a mechanism for acceleration as well, because if there was a mechanism associated with acceleration, then those two accelerating at the same time would actually experience the same time. But in this case, it's a co-effect of being in an accelerating frame, according to Einstein, with some distance separating the two. And the bigger distance that separates the two, the more pronounced the time dilation between the two objects. So we've got some problems with Einstein's resolution here, because in our quest to understand what time is and all the different factors that go into determining what causes time to speed up and slow down, we want to make sure that the entirety of this theory of relativity is consistent within itself. Simulated gravitational field and traveling twins turnaround does not produce the same light signal pattern as the original elevator model, right? The original elevator model, if you remember correctly, was traveling as a unit. Both things were accelerating. So as it was accelerating in the upward direction, for example, one of the ends of the elevator was traveling away from the opposite generation of light signals, and the other bottom end of the elevator was actually moving toward the light signals. So this was our gravitational or acceleration frame showing that our second type of mechanism produces an equal but opposite effect, which again is different from special relativity, which is equal and identical. But in order for this equal but opposite effect to take place, it made sense in this elevator example where one was stretching the signals because it was moving away and the other one was compressing the signals because it was moving toward. So that makes sense. But then when Einstein introduces this acceleration or pseudo-gravitational field in explaining how everything is accounted for in this paradox, the light signals do not do what they did in the original 1911 example. Because what happens is when this is in the state of turnaround, it's feeling gravity, and when it's slowing down and then speeding back up, it's actually causing a blue shifting of the signals. It's now accelerating and moving toward the existing signals, but it's also generating signals that are compressing on their way to B. So actually for both of them, they will both experience a blue shifting, and we don't have that equal but opposite effect that we did in Einstein's 1911 elevator example. So this is a big problem. Produces blue shifting of signals for both parties, which does not adequately explain the equal but opposite outcome. And I should say that when I first read about all of this, it was a huge problem for me, and I started doing a lot of reading during various pieces that were written in various decades. Again, this theory has been around for since 1905, but even since 1918, we're approaching 100 years on that. So in almost every decade, there's been a lot written about relativity, and I couldn't find anybody else that had a problem with this, because it appears that the rest of the scientific community was pretty accepting in the fact that once this gravitational field was induced, then we would treat it like a gravitational field, and anything far away from that gravitational field would be a higher clock example, and the gravitational field would be lower. But my concern with it was that the state or the act of acceleration was actually the mechanism behind inducing the shifting of these light signals to begin with, which would be synonymous with the changing of the clocks. So when you've got one end shifting them to blue and one end shifting them to red, that is consistent with having an equal but opposite effect. In the case where the ship is turning around here, we don't have the same situation, because these two are not operating at a fixed distance like they were on the elevator. On the elevator, they were at a fixed distance, and they were traveling as an accelerating frame, as a unit together, and it was very direction dependent. We got a blue shift in one direction and a red shift in the other. In this case, we have one party accelerating, the other party is stationary, and the distance is actually varying between the two, and that actually, like I said, produces a symmetrical blue shifting for both. So it would be very difficult to use Einstein's 1911 example to use this as a resolution to the twin paradox with two clocks in motion. Okay. So I found it hard to believe that I was the only one out there who had a concern with this. This traces back to, again, the 1911 paper that he wrote on the principle of equivalence, and where he states for AH, and we could easily put in GH there, A would stand for acceleration, G would stand for gravity, and H would be the height or the distance between the two. We would substitute in the gravitational potential. So essentially, in this particular case, this is one term that results from multiplying these two terms together, and assume that the relation which we have deduced for the homogeneous gravitational field also holds for other forms of field. So in other words, there's a lot of different things that are out there that we could call gravity. We could call a real gravitational field here on Earth gravity. We could call a state of linear acceleration gravity, and we could even call circular motion gravity. If you're on a merry-go-round, you're kind of pushed to the outside of the merry-go-round. If you're feeling a force because of a change of direction, that's another acceleration that's felt, and another simulated gravity experience. But what Einstein did, and I think carelessly, was once he equated this time dilation phenomenon with one type of pseudogravity, he just assumed that it would be applicable to all other forms of gravity, and I think there's a mistake in there somewhere. Okay? The cause and effect is not consistent. Again, with the 1911 example in the elevator, the actual act of acceleration induces the light signal shift. So there's a very distinct cause and effect relationship there that's not followed in other examples. Twin paradox as an example. Well, it turns out that after a lot of research and a lot of digging, a few months ago, there's a book called The Logic of Special Relativity, written back in the 60s, back in 67. S.J. Prokovnik, I hope I'm getting all these pronunciations of these names right, and he had a problem with this too. And he said, in explaining R.C. Tolman's example, or reviewing it, he said, one might expect that the variation of the Doppler effect during the reversal, turnaround here, period, would also affect R's reading of M's clock, since this effect is a reciprocal phenomenon, meaning symmetrical, the same. Depending only on the relative velocity. No reason is given for ignoring this aspect of the principle of equivalence. In other words, there appeared to be some inconsistency here. There was one set of facts that were used to explain a phenomenon in 1911, and that same set of facts was actually used on this 1918 example, even though the two examples did not equate.